Welcome everyone. Bonjour tout le monde. Mon nom est Pierre-Olivier Pinault. I will just be opening this webinar. We are happy today to welcome Dan Assouline to speak about machine learning for renewable energy applications, large-scale potential mapping, and electricity demand modeling. Dan is a data scientist at Unisanté, currently in Lausanne. He obtained his PhD from École Polytechnique Fédérale de Lausanne in 2019. And we are lucky in Montreal because he will be coming to do a postdoc at MILA, the AI research center in Montreal, starting in March. So he'll be presenting for about 40 minutes, and then we will have a Q&A session. Please write your questions in the Q&A box that you see at the bottom of your screen. It will be easier. We won't look in the chat, at least initially, if for questions. We'll really look into the Q&A box for questions. And if possible, and well, depending on the number of questions, we'll invite you to ask your question orally, but initially, please write them down in the Q&A box. So Dan, the floor is yours. I'll stop my camera, and then we'll be able to see you. Thank you for being here.
All right. So thank you very much. Thank you for being here, everyone. Thank you for the invitation. So yes, I will be presenting some machine learning applications for renewable energy. So large-scale potential mapping and electricity demand modeling. So it's basically my PhD work and a bit of a postdoc I also did in EPFL. So I will first show you some machine learning. I will talk about some machine learning broad concepts and some methods that I used in the work that I'm about to show you, so that you can understand a bit more, and it gives you just like a small array of some methods that are useful. So first, I'll present the spatial-temporal energy potential estimation. That's part of my PhD thesis at EPFL in Lausanne, and then I will show you some projects about electricity demand modeling that I also did with some machine learning methods, and then a conclusion in a future. So, okay, first, what is machine learning? So I'm sure you heard of machine learning in some shape or form, but it might seem magical from outside. So basically, it's not magical. You just need data, okay? So from a set of measurements, the idea is to learn a model without an a priori on the shape of the model. So that's the difference between, you know, with maybe classical statistics. Now they really fuse together, but it's kind of one of the difference with classical statistics. Like, you know, you try to fit a line. In this case, sometimes you have an a priori, sometimes you don't have an a priori at all, and you just let the data completely speak for itself. And you want to try to understand and predict a phenomenon. So finally, what are machine learning methods? They can be defined as algorithms that improve the performance with experience. You feed them experience, meaning you feed them examples of the data you want to model, and they learn from data. So the more you have the data, the more you capture all the phenomenon, and the more you can model it and predict whatever you want to predict. So feeding the model is training the model. Fast example, for example, in 2 dimensions, let's say you have a set of animals and you have only 2 variables. You have their weight and how furry they are. So you have their fur density. So that's the data. That's your input features, weight and fur density. You want to learn a classification function. You'll see that classification is a very typical thing you do in machine learning. And you want to classify between tigers and lions. So the only thing you have is the weight and fur density. Can you really say the difference between the two? The data will tell you it might not work, but that's what machine learning can do for you without an a priori on what's the form of the separation between the two. So there are mainly 4 learning frameworks in the context of machine learning. The first one is called supervised learning. It's basically when you have some examples of the output you want to model. So let's say, for example, you want to say that in this 2D plot here, X2 is the fur density, X1 is the weight, the blue points are lions, the orange points are the tigers. Very, very separated. You learn from examples. You know which point is a lion, which point is a tiger. Okay, and you can do classification like this, or regression, which is instead of predicting a class, like 0 for lion or 1 for tiger, you want to predict a function. So let's say, I don't know, let's say you don't have the weight and you want to predict the weight. It can take any value. So that's supervised learning. That's what works the most. There are cases where you do not have the output. So for example, you have 100 animals, but you don't know which is a lion, which is a tiger. So the data is called not labeled. In this case, you can try to learn from the input points only. So let's say you have this, like this, you just have a bunch of points. And for example, what you can do is clustering, meaning that you try to find groups of points only by the distribution of the input. So in this case, instinctively, you can see that there are like 3 blobs, and there are some methods that try to separate these blobs and tell you, okay, there's a good chance that these are 3 different groups. This is unsupervised learning. An interesting other framework is called semi-supervised learning, where you have some examples, but only for a very small number of points. And you can use both examples and the point that are not labeled to try to have the best, for example, classifier possible, the best classification function. In this case, if you have only these 6 points, that will be the separation that is the most natural between the two. But if you add other input points, which you don't know the examples for, you suddenly, they guide you into having a better classifier. That's an interesting thing, but it doesn't always work. But it's just interesting to know that there are some methods that do that. And the last one is called reinforcement learning. It's a very different kind of, let's say, framework, where instead of learning from data that is already there, you basically, it's a die and retry strategy in the way that you try some experiments and you see how close you are to your target. If you're close, you give a reward. If you're not close, you give a punishment. And you try, and you try, and you try, and you try. It's basically like a baby, touching fire, this is not good. Touching this is good. And it works quite well. It's really used in robotics, for example, but in my case, I won't really show you examples of this, but it's good that you know what it is. In machine learning, it's a very used thing nowadays. Now we'll show you 3 groups of methods, let's say, that just because I use them in the things I'm gonna show you later, so that you have like some view about them. Also because I think there are I will show you like a benchmark method I use a lot for supervised learning, let's say classification and regression, a clustering method, and then I'll talk about neural networks, which are kind of the deep learning, which are very used nowadays. So the first one I will talk about is called random forest. So random forest is basically an algorithm that basically has an idea, trying to train multiple models that are not very good on their own, and basically train all of them and average the prediction of all of them. And just the way of averaging this prediction basically reduces the variance of the prediction and it makes it better. And you can use this with all kinds of algorithms. You can try 100 linear regressions and average a result. But in this case, they use trees, so decision trees, which are models that are they're not very, very precise, but they're very fast. And basically, they just separate the domain into rectangles, saying, okay, if the Frey density is less than 10, you go left, otherwise you go right. And you separate your domain in rectangles like this. And then once you have a new point, you make it go through the tree. It arrives into a rectangle, and the prediction for this point is just the average of the points that are in this subdomain. It's a very, very easy model. But in this case, what random forest does is it trains 100 of these trees, take the prediction, average it, and it adds some randomness to it also, which makes it even better. And so yes, once you have your forest, so multiple trees, you pass your new point through the thing. For less than this or bigger than this, you go left, right, left, right. You arrived into a leaf. In here, you have some of your training points. You take the average of the points and you have your prediction. And this is actually a very fast method, very easy to use. You don't have a lot of parameters. It has a lot of practical advantages, like it can handle outliers and different kind of outputs. It can extract some uncertainty. I'm using it a lot because it has a lot of practical elements and it's quite precise. There is a random aspect to it, so you might want to use it to train multiple times and average on top of it, average the accuracy or the performance, because it doesn't give you exactly the same thing every time, but it's very useful. A quick method for clustering that I use a lot and that is quite useful. It's called DBSCAN. Of course, I won't show you, all the methods that exist. There are like a lot of different things, but this is one method that I think is very useful. The idea is very simple. You want to define clusters as dense areas of points separated by low density areas. You can see that as basically islands separated by water. The water is the low density, and the islands are regions of high density of points. And this algorithm basically detects this. And then if a point is alone in the noise, in the water, it's detected as an outlier. So I won't go into details of the algorithm, but you have multiple parameters. You have the radius of the neighborhood. You have the number of samples, that is the minimum number of samples in a neighborhood. And if you change this parameter, for example, this epsilon, you will find groups that are more or less dense by choosing the radius. For example, here the radius is quite large, so it finds these two groups together. And then if you move it, you find the three groups. If you move it too much, then you start to find subgroups of the big groups. So it needs a little bit of tuning, but it's very useful. And it detects automatically all the clusters. You don't need to say, okay, I want to find 5 clusters. You might have heard of k-means, which is the ultimate classic benchmark clustering algorithm. In the case of k-means, you need to say k, so you need to say how many clusters. In this case, you don't need, and it detects outliers. So yeah, it's a good algorithm. It's only for fixed density clusters, and some parameters are hard to tune, but it's quite good. Okay, these are the two methods. And then last but not least, very quickly, because I used it in my postdoc, neural networks. So AKA deep learning nowadays. And Montréal is a very, very high place for deep learning. So I had to talk about it a little bit. So what is a neural network? It's a highly nonlinear parametric predictive function that mimics neurons of the brain. So it's trying to copy the architecture of the brain. So how do you build a neural network? You start with a linear function, which is called a neuron, continuing the metaphor of the brain, y equals ax, okay? It's very stable, it's very easy and fast to compute. And then what you do is you add a nonlinearity after it. So an S-shaped function, just like this. So there are a lot of functions that do this. But more recently, we found this function. I mean, it's been years ago actually, but let's say it's recently, in the 5 to 10 years ago, this function called ReLU, which is just this. So it's a very, very easy nonlinearity. So instead of having a nonlinear function, you take a function and then you put a nonlinearity after it, and you stack this one after the other, and basically it gives you a neural network. If you want to see the more classical way of seeing it, so X is multiple features, you can stack multiple neurons, and you have something like this. Here you have the inputs. So let's say you have fur density, weight, etc., etc. Here you have the output, so 0 and 1 for lion and tiger. And in the middle, you have a hidden layer of nodes, which do not really have any physical meaning, and you can put many of them. It's just that this is expressed, basically the output is expressed as a linear combination of this, which is expressed as a linear combination of this, etc., etc. So it just allows you to basically express a function as complex as you want based on this. So again, it tries to mimic the brain. So you have the axon that propagates the information. This is a neuron. So this is basically one of these blue cells here are like this. So you can see that it's expressed as a linear combination, sum of W, X plus B. And you can have any number of hidden layers. Okay, so basically at the end, each arrow has a weight. It's a linear regression, and it's like a beta that you want to find, and training the neural network is equivalent to optimizing all the weights. You want to find all the weights, and at the end, you have just a bunch of linear functions that you put next to each other, and it gives you a nonlinear function. It might seem a bit obscure, but it's actually very, very useful. So what is deep learning? It's just a neural network that is very large, so with a lot of hidden layers, a lot of parameters, and if you need the computational power. So it can theoretically model anything. There's actually a mathematical theorem that says that. If it's big enough, it can model anything, any kind of function. It's very good notoriously for important applications like text, audio, image, face recognitions, speech recognition. It's useful for many tasks, classification, regression, clustering, etc. For example, detecting kittens or any kinds of things on a picture. The interesting thing is it's an old idea. It was invented in the 40s, and then a lot of different ideas came. But the thing is, at the time, we didn't have the computational power. So now it works. We didn't have that much data, but now we do. So now it works better. And of course, because it started to work, we had a lot of research, again, including in Montreal. So nowadays, it's really the state-of-the-art machine learning algorithm. It's basically, it gives the best performance. It's very versatile. The problem is it requires a lot of data, sometimes manual tuning. So you need to decide on the architecture, and it can be anything. So you need to try different things, and it takes a long time to train. It could take days to weeks, etc. The types of deep learning algorithms, there are so many. The multi-layer perceptron is the one I showed you, basically, just with the typical structure. One I talk about very quickly is called convolutional neural networks. It's I used it, so you will see some results with this. It's basically it's useful for image processing. Let's say, for example, for automatic recognition of handwritten letters or numbers. And basically what it does is that it uses operations called convolutions. And with this, it extracts features directly from the image. So you don't decide on the feature. It's basically a window that goes, it's like a window of a certain dimension that goes through the image and extracts features of the image. It can be edges, colors, points, etc. And it's a combination of convolution, and then you change the dimension, you do a convolution again, and it extracts all kinds of features. And then at the end, you put a normal neural network and you train on this. And it can do a lot of things. It's really the state-of-the-art network for image processing. It's very useful. There are other ones that are used for time series prediction, for other kinds of things, but I won't go into details because I've been speaking of this too much and I need to talk about energy now. This is all kinds of architectures that exist. Okay, so that was machine learning. Now we go into the application. So machine learning for spatial estimation. So again, this is the work I've done during my PhD. So what is the motivation? Of course, we have, kind of an issue here in terms of climate, CO2 status. So a solution is to try to increase the use of renewables. Installed renewable power is indeed increasing. I am in Switzerland. I did my PhD in Switzerland, so I studied the Swiss case. But it's not enough for goals like the COP 2020, etc. And the Energy Strategy 2050, that is something in Switzerland. To maximize the use of renewable energy, it would be nice to have a potential estimation at a large scale of countries. Basically, knowing how much we can have if we install systems everywhere we can. So, for example, for solar energy, for geothermal energy, for wind energy, we would like to know how much energy we can extract from systems. So all three are deployable at large scale and they're theoretically known and studied. So I chose them for my PhD research. These are the production that was in 2017 in Switzerland. So it's not a huge amount. For example, 1.68 terawatt hour per year in Switzerland with all the PV panels on top of rooftops. The idea is there more potential? There's probably more, and I try to estimate how much. So my research goals were the following. So can machine learning be combined with traditional models, because you still need to know how the solar energy, etc., works to predict potential values? And what is the potential in Switzerland? So basically there was kind of, how do you do this? And what is the potential in Switzerland? And then you can basically try to estimate this potential for these energies and either for other energies using the same method I'm about to show you in pretty much any location that you want. Quick thing, there is something called a hierarchical methodology for potential estimation. So there are multiple levels. The theoretical level is the maximum potential provided by the source. So for example, the solar radiation that arrives on the ground or on your rooftop. The geographical potential basically reduces the potential to the amount where you can install the system. Let's say the PV panel on top of your rooftop. There's a limited space for that. You cannot just take all the space. And then a third layer is called the technical potential, which is that it reduces again the geographical potential by taking into account technical aspects like the conversion rate, the performance ratio of the panels, etc., etc. There are some other levels that I didn't tackle: economic, which take into account cost considerations, and market, which takes into account additional constraints like regulation, policies, etc., etc. So if you want really to know exactly the amount you can install, you want to go until the end. But I stopped at technical because it was the most important, and then I had to finish my PhD. So general method for estimating the potential for one energy, let's say solar, is as follows. So yeah, I will just put all of this because this is a heavy slide. It's as follows. So first, I listed the needed variables. There are multiple ones. There is, for example, radiation, space on top of rooftops, etc., etc. And for each variable, I apply the following block of estimation. So first, you collect the data, meteorological data, height, all kinds of data that is related to, let's say, solar radiation. Let's say that this variable is for estimating solar radiation. Then you extract examples of solar radiation. So with meteorology stations, for example, you select features that are useful. So let's say, again, altitude, temperature, etc., etc. Then you can train a machine learning model that learns the patterns of solar radiation and basically predict for the rest of the areas where you don't have solar radiation. And at the same time, you can predict uncertainty of the prediction. And there you have your map where machine learning basically filled the void where you didn't have your solar radiation, but you had other information about the altitude, et cetera, the feature. And then you can do that for all the variables that you need, and you combine them into, might be physical models, into the potential, the final potential, for example, for solar radiation. So I will show you a bit more details for solar potential estimation, and I will show you just the results for the two other energies because there's not enough time. So there are some maps that existed in Switzerland already, but with low precision, and the methodology are mainly very crude based on simple coefficients. So I wanted to estimate really all the electricity you could generate from PV panels over rooftops, only over rooftops and not everywhere, because otherwise, I mean, it's very, very big. And at the scale of pixels, which are 200 by 200 meter square pixels, and also in communes over the entire Switzerland. And again, the strategy is to try to estimate the different variables that are related to solar radiation, and then extract all the available information and fill the gaps with machine learning prediction where we don't have these variables, for example, random forest. So what are the variables to estimate? First, solar radiation, then the available rooftop area for PV, like this. You cannot go until the end, etc. There are some restrictions. The geometry of the roof, because based on the tilt of the roof, the how can you say, how they are, the direction of the roof, sorry, the solar radiation is not the same. You have to take account into of the angles. And then the shading over the roof. If there are obstacles next to it, etc., you need to take account the shading. And then you can combine that into a tilted radiation, meaning the radiation that arrives in over the rooftops with the right angle, and then extract the potential. What are the features that I use as inputs for machine learning? So there are all kinds. Space features, so latitude, longitude, and altitude. Meteorology, so sunshine duration, precipitation, cloud cover, etc. All kinds of building information that I needed for the characteristics of the buildings. So this is all the information I could get from Switzerland. You might not have access to this data everywhere, unfortunately. In Switzerland, I was lucky, you have a lot of data that is kind of public, but I had to make a lot of phone calls basically to have all this data. And finally, building shape features, so geometrical features, the elevation, so the altitude of the buildings, etc. So there's a lot of things. So for example, the first variable was the solar horizontal radiation monthly. So how much sun arrives in a horizontal ground in a month. So the strategy, again, is to learn from monthly data across the country from a few stations that I have and extrapolate. Meteo, space. I have my examples of horizontal radiation, and then I can learn a random, I can teach a random forest to learn these patterns, and then I predict my horizontal radiation for all the months, because I have the data, I have labels for every month. I can extract a performance error. So in this case, there is global radiation and diffuse radiation over my rooftops. And this is the error. So it's about 5 kilowatt-hour per meter square of error. And there's a prediction interval that is attached to it. So this is how I get my maps of solar radiation. And you can do the same, basically, with the same idea for any kind of variable. So the other variables I needed, again, is the available rooftop area on top of PV. So I learned from the Geneva canton, because in here I had a lot of data. Exactly, I knew where the chimneys were, et cetera, et cetera. So I extracted available area in Geneva, and then to do this, I had to simulate the presence of PV panels. So with a geographical information system software, I had to install these panels at basically little rectangles, taking account the slope. So that's why they don't have the same dimension, and basically computing the area that is available. And then you can extrapolate this. The same for the shading factor. I computed the shading with the software. There are 2 shading factors, but it doesn't really matter. And then you can, again, extrapolate. And last but not least, the rooftop characteristics. So I had to do multiple classifications to basically estimate, in the case where I didn't know, the shape of the rooftops. So there are some, normal ones, there are some pyramidal ones, there's a lot of different types of rooftops, the direction and the slope. And once I have all of this, I can combine into a potential, into a final energy estimation. So this is, for example, after taking into account a few technical aspects like the performance ratio and the efficiencies of PV panels. As you know, the efficiencies of PV panels are not great. I mean, they can be around 20, maybe 25%, but not more. This is like a conservative estimate. And here you have in a pixel for all the months, the potential in megawatt hour per month, but the maps are quite small. So you can see better in the yearly version, where you have basically, for each pixel, the potential. The black pixels are pixels where you do not have urban areas, so no building, basically. So you do not have a place to put the PV panels on top of. And here you can see all the buildings. So this is in megawatt hour per year. And I did the same kind of strategy for, I'm sorry, this is the normalized version per capita. So of course, you have less potential in Zurich because there's more people. So you don't have, you don't have the same amount of LRG per person. But it's still, it's always useful to know per capita, because otherwise you don't really know what you have at the end. And I did the same for geothermal potential. So for shallow boreholes, more precisely, I tried to extract the heating potential in megawatt hour. So yes, giving the same amount of maps, trying to put the boreholes anywhere it's actually makes sense. And I did the same with wind potential, trying to estimate the wind speed everywhere in Switzerland and to virtually install wind turbines everywhere where you could install them. And again, you have a potential. So in this case, it's a power, it's in kilowatt. So yes, so that was basically my PhD work. So yeah, basically I managed to extract some potential. The problem is it's hard to find a ground truth to compare to. There are some studies that have been made and you can compare with them, but it's quite hard. It's generalizable to other countries if you have the data. It's useful for strategic planners, et cetera, et cetera. So in Switzerland, there is a serious potential. So for example, for solar now, there's 1.7 terawatt hour installed, but I estimated, and it's a pretty conservative estimate, 16.3. So basically there's like a factor of 10 of potential that we don't really take profit from. So yes, there's a lot of potential. Okay, so now I will go to the last part, which is electricity demand modeling with machine learning. So what did I do? There were basically two small projects I worked on during my postdoc. The first one was to try to detect anomalies in electricity demand in buildings, in commercial buildings. So the objective is to try to find anomalies in electricity load curves in commercial buildings. This was a project that was, we were kind of like a small consulting for a telecommunications company in Switzerland. The data we had was 15-minute electricity demand, so in kilowatt hour, for about 600 buildings. And they wanted us to say, okay, for this month, this is normal. For this month, this is not normal. There's an anomaly. There's something wrong in this time series. So we thought of two methodologies. The first one was a supervised strategy, trying to use basically image processing. So the idea was to say for each month, so if we want to say that each pattern is normal or not monthly, we put basically the days of the month in the x-axis, the 15 minutes of the day in the y-axis, and then for each month, you have basically an image that describes the load, the electricity demand for the entire month. So here, of course, this is during the day and this is during the night. So you have less electricity demand during the night, and then these bars are Sundays. So we thought, okay, it kind of makes sense. You should have a typical image for normal electricity demand. And then you can use, for example, convolutional neural networks, which I talked about, to say, okay, this image is normal, this image is not normal. If you train, so you hire, basically we had experts that labeled a few images, I mean like thousands, saying this is normal, this is not normal, you should be able to learn. The second strategy was an unsupervised one, trying to detect anomalies directly in time series. So let's say, for example, this is again the electricity demand in kilowatt hour every 15 minutes. So each peak naturally corresponds to a day. This is an entire month. Each peak corresponds to a day. And for example, here is a weekend, here is a weekend. Here, for example, there's something wrong. It should go until the end. This is a Sunday. So trying to detect the anomalies in the peak, or if there is a peak and it shouldn't be one, or if there's a valley and there shouldn't be one, trying to detect this directly in the time series with time series analysis and machine learning. So the first method, again, was with images. So we had images that were labeled by experts of the company as good, like normal, or bad, abnormal. So it gives us this. If you put it in a small format, for example, this is like a typical image. This is a normal pattern. The colored one, like the green, is like normal during the day. And then the bars in between are weekends, etc. But then there were interesting patterns that were still classified as good. For example, this, which seems a bit weird to me, but the expert tells us that is good. So that's why, in machine learning, if you do supervised learning, you always need to know the truth and have someone that actually knows the domain to tell you, okay, this is a good pattern, this is a bad pattern. So we had images like this, and we really treated it as images, as photographs, just pixels. Problem was, it was a little unbalanced. So there was 2,500 normal patterns and about 1,500 bad patterns, so abnormal patterns. And actually, if you have an imbalance like that, the machine learning algorithm will tend to predict everything as the majority, basically, because then it will see that, okay, the performance will not be as bad if you do that. So very quickly, the CNN results, of course, I won't give you the detail of the architecture, etc. But the thing is, the training error and the testing error goes down, meaning that it works with time. To update the weights, you have to run like multiple optimizations, and it goes down with time. Of course, in your training data, when you know everything, it can go down very, very, very down. And in the testing, at some point, you arrive to a limit. But it still works. And what I found is when I use all the images, because of the imbalance, the lack of balance, I found 97% of the good images as good and only 10% of the bad images as bad. So that was a bit imbalanced. So I tried to kind of rebalance things by using an equal number of good and bad images. And you rebalance things, but then it's still not very good. So 45% of good images were classified as good and 74% of bad images were classified as bad. Unfortunately, I couldn't really continue this project. There are some people that are working on it to try to improve it. The second method was a time series analysis again. So the idea was to extract basic time series features for each week and apply clustering to detect multiple patterns and outliers. So the technique was really simple. Basically, we had the time series for the entire month, and we could separate into weeks. So we have a time series for each week. And we apply Fourier analysis to basically extract some features of the time series. The mean, the amplitude, the different modes, etc. If you know signal processing, Fourier analysis is really, really classic. So you can extract multiple features. And then we try to project that in 2 dimensions using PCA, principal component analysis, which is a very famous projection method that reduces the dimension while keeping the same information, basically. And then I use some clustering on that. So in this case, DBSCAN, to try to detect clusters and outliers. And the results were like this. So this is an entire month. Again, each peak should be for 1 day. So this, sorry, actually, this is not an entire month. This is 3 different weeks, just, sorry. And the results of this method of the projection give us this. So it's pretty good. The black points are detected as outliers. And you can see that it's for weeks. So this week corresponds to this point that are very weird. So it detected it as outliers. The blue basically group are the normal group. This is perfectly normal. And then the orange points was again detected by the algorithm as a different group that are kind of anomalous. There's something wrong here, but it's not as abnormal as this. So basically, we were like able to detect weeks that were normal, weeks that were kind of abnormal, and weeks that were like very weird, basically like 1 day or 2 days missing of electricity data. The second project was very, very close. It was just, okay, it's hard to detect anomalies. So let's say that we just want to do some clustering, just try to detect patterns of typical load, so typical electricity demand. So we have our buildings, we have the whole years of electricity time series that look like that, for example, again in kilowatt hour. Each line is a time series and corresponds to 1 building. The idea is, okay, let's try to make different groups, let's say, I don't know, 4 or 5 groups of buildings with similar electricity demands. Then we can maybe treat them differently, etc. So what I did is I used the exact same strategy as I used here, basically the clustering. But in this case, I wanted to detect anomaly. And in this case, I'm just going to directly detect the different groups. And it kind of works. It gives this. So each subplot is basically a different group that is given to me by DBSCAN. And I just, superimpose all the time series for the electricity demand. And I just computed the mean of all the time series in this group in yellow. And it kind of make groups that, make sense because they have kind of the same shape. Of course, then there is a big group of outliers here. But then when you use DBSCAN, you have to choose if you want to, find groups that are very dense and you might find a lot of them, or if you're kind of more relaxed and you might have more heterogeneity in your groups. But in this case, it kind of worked. I mean, in any case, the company was quite happy, but it's a very, very simple kind of method. Okay, so with this, I'm going to conclude. So just future outlook, there's a lot of things we can still do on the work I've done. So for the for the spatial estimation, we can work on uncertainty propagation because it's a long methodology. So this kind of an uncertainty that propagates through the entire method. We can try to tackle the economic and the market potentials. We can compare with demand. We can try to see a hybrid combination of the different energies I estimated. And actually, there's another PhD student in my lab that did some of these things, that tried to continue what I did. For electricity time series analysis, so for the second thing I showed you, there's a lot of things we can do: forecast future anomalies, apply electricity load clustering for households, because this was for commercial buildings. Yes, as it was said in the beginning, I'm coming to Montréal, so that's my future. And yes, I will work in Mila as a postdoc with Professor Yushra Benjo and Lubna Benabou. So yes, I will be there. So I'll look forward to meet you if you're interested in this kind of things. And yes, this is it.
Thank you very much, Dan. Very interesting. There are two questions already, so if you go in the Q&A, Dan, you can.
Yes. So Q&A. Okay, I have to stop the
sharing your screen.
Sharing my screen, exactly. Okay, so Christian asked, very often the data include errors like negative solar radiation due to data acquisition malfunction. Do you need to clean up the data before you apply ML methods? Yes, you do. Actually, so this is a good point. Unfortunately, machine learning from outside might seem very sexy and very useful and very interesting. It is very interesting, but the reality behind it is that there's a long time that is dedicated to processing the data. So yes, you need to clean the data very thoroughly, and depending on the algorithm you use, you might have to put the data into a certain format. You might have to exclude outliers, which are basically points that have a value that are very different from the others. And you have to, yes, basically exclude things like negative values, like things that don't make sense. So yes, you do need to clean up the data, and you need to do it very carefully, because if the data is not good, the algorithm is not going to learn basically anything very useful. So yes, that was one question. If you want more details, please don't hesitate to ask me. And then Abdelaziz asks, did you consider using variational autoencoders for the anomaly detection problem? The deviation between the actual and reconstructed data can give an indication on the outliers. Yes, so there are a lot of different, there's a lot of different algorithms you can use for this. So for example, deep learning algorithms. So yes, I heard about autoencoders, but I never really used it. Basically, one idea we had was to basically try to detect very, very localized anomalies, where to try to, basically do forecasting, like predict, try to learn from one part of the data, predict the rest, it gives you something, and then you compare the reality with the rest, and you see if, there's a peak that shouldn't be there, et cetera, et cetera. And that worked quite well if the data is quite regular, for example, like the data I showed with the one peak for one day. But yes, to answer your question directly, no, I didn't use VAEs, but it could be interesting to use. I tried some methods like LSTMs for forecasting to do what I just described. But VAEs I didn't try to use, which generates the data. Yeah, but I might look into it later. So thank you for your question.
Please, if you have any question, you can raise your hand, and I can give you authorization to speak. So don't hesitate to raise your hand if you want. Dan, I will ask you, in terms of commercial applications. Have you seen some companies actually in energy actually using some of the ML techniques to develop a market or to analyze the data and to empirically and commercially do analysis?
So yes, there are definitely some there are definitely some companies that try to use machine learning, but not really. For example, for the spatial estimation, not exactly. I mean, the big thing when I started my PhD in 2000, I mean 1 year after my PhD in 2015, actually, I don't know if you remember, and I don't know if it's still alive, but Google actually launched a platform that would, I think, just called Google Solar to detect, to compute the potential for rooftops for PV. And yeah, of course, they use some machine learning for that on top of just the geography, because, they have, of course, a lot of data. So yes, there are some people that use these kind of things. But I have not seen, like a commercial software, but it should exist. I don't know, that gives you really the potential. There are some things that exist that give you the potential over your rooftop that would compute, but this doesn't really use machine learning. You just give your data, you give your space, etc. But that computes the potential over entire countries. There was some research, but I haven't seen really commercial.
Because I guess for PV companies who want to do some very targeted marketing, they could basically almost knock on the specific doors. After doing what you've been doing, they can identify which are the neighborhoods with the best roof, with the best solar insulation, and then do some targeted marketing. So I guess that would be the direct application for either companies or governments that want to place provide subsidy to the best locations in terms of PV.
Right.
So they could say so in specific regions, that's where we should focus our efforts, because this is where the biggest potential is.
Yeah, that's true. Yes, in places where they build, they should. Yeah, it's true. Maybe I will think of, selling my maps.
in your wind potential was relatively, I mean, it was 10 times bigger than the actual generation of wind in Switzerland, but the wind generation being so small, you have a really small wind potential. So what kind of rules did you use to exclude? Because I'm pretty sure the physical potential is bigger than that.
Yes. So yes, there's a lot of things about wind. So first, there is a common thing that people say is that small turbines are useless because they don't have, for example, small turbines on top of rooftops. Because they exist, they don't have a potential, but actually they do. It's just that, of course, because of basically the obstacles of the urban area, there's like a whole theory of different layers of roughness. We call it roughness. It's basically the zones where the wind behavior is kind of chaotic. So on top of urban areas, it's hard to model really the wind speed. So there's like a logarithmic law if you go high enough, but if you're close to urban areas, it's hard. There are some equations that gives you kind of the model, but it's kind of hard. In rural areas, we really know how to model the wind, and we really know how the speed increases from the ground until the air. So, and that, of course, the most important thing for wind is how they, so of course the speed, the wind speed, and how turbines are close to each other. Because if they are too close, then it doesn't work, etc. So there are some wind farms. And so basically what I try to do is two things. Install virtually, again, of course, big turbines, so commercial turbines in rural areas, with a rule of thumb, basically with, like a fixed spacing. I don't exactly remember. I think it's 7 times they should be in between two turbines. They should be 7 times the diameter of the turbine in terms of length. Otherwise, there's like a chaotic, behavior in between. So install this, and I also try to install some small turbines on top of the rooftops, but in the periphery of the urban areas, just to see how much potential you can have. But then, of course, you know, I mean, it will cost a lot of money to install all of these wind turbines. So it's just, you know, for people, it's just maybe not worth it, because it's not maybe as efficient as and as cost effective as solar panels. So there's a lot of different, you know, a lot of different restrictions you have to use when you compute wind. Yeah, and in Switzerland, I mean, my potential was 10 times, because in Switzerland, there's really not a lot of turbines installed. There's literally, I think, 15 or 20, there's really few. So that's why my potential
But I
was
mean,
big.
the potential you write are depressing, because, you know, it's so small. It cannot
I know.
possibly cover the actual electricity consumption.
Yeah, that's true. But if you add everything on top of each other, you see what I mean? So, for example, in Switzerland in 2017, the demand, the electricity demand, was about 60 terawatt hour. Okay, so if you take my potential, which is, let's say, 17 terawatt hour per year in solar, you have 25% of the demand. It doesn't cover everything, but it's still, you know, if you have the 25% and then you add the geothermal and you add the wind,
Okay.
you know, then, I mean, you have something. It doesn't cover. It's very hard to cover the entire demand, to be like full renewable. It's hard. It would take some time, and it would take, you know, with PV, for example, the good thing is the performance ratio, the efficiency of the panels, they really increase with time. So now we have more and more efficient panels. But
Yeah, but there's an upper limit. I mean, you said,
yeah,
but they cannot go beyond 25% or something
yeah,
like this.
yeah, it's hard. Yeah.
Abdelaziz Amash is asking, why do we limit the PV installation to just rooftops?
Because it's just, I mean, yeah, it was a first step, basically. It's just that it's a common thing, and you know, it's kind of, it's really area that you're not going to use for anything else. So it's just a very good use of this area, and it's a very common thing. Of course, you can just put, you know, panels in the ground. I mean, there were some studies, you know, there were some like PV farms in deserts, etc. You know, if you cover the entire Sahara Desert, of course you have a lot of potential. But in Switzerland, you know, we don't really have spaces like that.
Lakes, you can use some lakes.
You can use some lakes, but then the lakes are already used as, you know, geothermal energy, basically. In EPFL, one of the biggest amount of energy that's actually used in EPFL is quite cool. They basically take some heat from the lake, and it works pretty well. But yes.
I would have another question. I mean, you mentioned that you need a lot of data, and so that was clear, and that you also mentioned that we need to clean the data. But my question is more on the availability of data, and in general, do you think there is enough publicly available data sets so that all the ML research can actually be public, or is it bound to be more private research? For example, the examples you gave on the company who had like the 600 buildings, the consumption of 600 buildings, you need to have that, and you know, it's only private information, so it will have to be most of the time some private entities that do the research, and they won't share, well, they will share what they want to share, and in many cases, so my general question is machine learning only restricted to private applications, or can we think of public applications because there's enough, or policy applications because there's enough publicly available data to actually use these techniques for public policy or for you know, transparent research?
So in my case, in Switzerland, there was actually, so this postdoc thing was different, but in my case, all the data I found, I used was actually public data. It was either, you know, owned by some research institutes or something, but so I had to make a lot of phone calls and explain why I want to use the data, but it was still public data. So I think there's a lot of things, you know, there's a lot of things you can still do. And the good thing is, you know, you don't need, that's the entire point of machine learning. You need some data, and the more, the better. But as soon as you have a decent amount of data, then you can do something. You don't need everything. Basically, without machine learning, you would need all the data. So you would need, all the buildings, you would need all the shape of the rooftops, etc. Machine learning allows you to fill the void. So it's kind of, but you need some starting
data.
Yeah. You need, without this, you cannot do anything. But yeah, I think there's more and more public data. You just need to know where to look, basically. But there's a lot of even publicly available, sites where you can download some data. I mean, a lot of data is in research, but I think there's still a lot of things you can do. Of course, companies have also access to other data, but yeah, that's another story.
Good, excellent. We still have 5 minutes. If anyone has a question, you can raise your hand and I'll give you the mic. Don't hesitate. If you have comments, also. Otherwise, I will thank you, Dan, again for sharing with us your expertise and applications. Very interesting. And for many of us, it was also very educational, because we hear as you say, we hear a lot about machine learning, but we don't get as many chances to actually look into real applications. And thank you for providing the introduction to your techniques. Oh, there's someone just quickly raised the hand, but then dropped it. Okay. Thanks, everyone. Thanks, Dan. The session is recorded. It will be posted on our website. And have a good day, everyone.
Thank you very much.
Bye-bye.
Bye-bye.